Welcome back to the podcast. Yovs, great to have you here again. We were just discussing the importance of data in algorithmic trading, and now we're diving into Chapter 3, working with financial data. This is fascinating. Can you break down the different types of financial data we're talking about?
Absolutely, Matthew. It's crucial to understand the various types of data you encounter in algorithmic trading. The chapter highlights that, while algorithms are important, the quality and comprehensiveness of the data are paramount for reliable predictions. The key idea here is that you can have the fanciest algorithm, but if the data is flawed, your predictions will be flawed.
So, we're looking at historical versus real-time data and structured versus unstructured. Can you elaborate a bit more on that distinction?
Right. Historical data, like end-of-day closing prices, is readily available from various sources. It's structured, meaning it's organized in a tabular format, which is ideal for analysis and backtesting. Think of it as looking at the past performance of a stock to see how it moved over time. Real-time data, on the other hand, is, well, happening right now. Bid/ask prices for currencies, for example. This is super important for live trading. Unstructured data could be financial news articles or tweets, potentially valuable but much more difficult to analyze in a straightforward way. This chapter is focused on structured, historical data.
And why is structured, historical data so central to the backtesting process?
It's fundamental, Monsieur. You need a dataset of past performance to test your trading ideas. If you want to see if a particular strategy would have worked profitably in the past, you need access to historical market data. The examples given, end-of-day prices for SAP SE, or intraday data for Apple Incorporated, are perfect examples. This chapter shows how to get this data and how to prepare it effectively for backtesting. This chapter emphasizes the structured historical data as the starting point for many strategies. Real-time data analysis is a different beast and is dealt with in Chapter 7.
So, the chapter is focused on importing, handling, and storing this historical, structured data. What tools and methods are discussed for this process?
Exactly, Matthew. The chapter's strategy is to equip us with different tools and data sources. It talks about using pandas, a powerful Python library for data manipulation. We'll learn how to pull data from various sources, files, websites, like Quandl. This is especially relevant because a lot of valuable historical data is available openly. It also mentions the Refinitiv Icon Data API, which is a paid service for professional-grade market data. The chapter also covers efficient storage methods using the HDFS, Hadoop Distributed File System format.
Wow, so many different tools and options for dealing with this data. That's something that's always beneficial when backtesting, having multiple choices. And I see they're emphasizing the Python 3.8 environment, a point we'll need to keep in mind as we move forward.
Absolutely. It's crucial to have a consistent environment. The chapter assumes you've already set up your Python environment, as outlined in Chapter 2. Plus, they mention Hilpish, 2018, ch. 9 for even more in-depth information on data handling with Python, which is a great resource to have in mind.
This is really insightful. Thanks, Yovs, for breaking this down for us. This lays a solid foundation for understanding how to actually begin working with the financial data in the context of backtesting. Hey, Yovs, welcome back to the show. We were just talking about the different ways to approach algorithmic trading using Python. Now, you mentioned the power of pandas, this popular data analysis library. Can you give us a bit more detail on how it helps with reading financial data from various sources?
Absolutely, Matthew. Pandas is fantastic for that. It's really a core component, in the Python toolbox for algorithmic trading. It excels at handling different formats of financial data, which is crucial for, pulling in historical price information, trading volume, market data, all that good stuff.
So, you're saying it's not just about storing and manipulating data, but also pulling it in from various sources?
Exactly. It's a very versatile tool for reading data from different sources, like CSV files, Excel spreadsheets, databases, and even web APIs. Different data providers use various formats, and Pandas makes it painless to work with them all.
That's interesting. Can you give us some specific examples? Like, how might you pull data from a CSV file, for instance?
Sure. You use the read_CSV function. It's incredibly straightforward. You just give it the file path, and Pandas figures out the structure of the data. Crucially, you can specify things like the delimiter, header row, and data types to ensure the data is read correctly, which is, super important for avoiding errors later on.
So, if the CSV doesn't have a header row or uses a different delimiter than a comma, you can adjust those settings?
Absolutely. Pandas is very flexible in these cases. You can use parameters like header equals none if there's no header, or sep equals \t if the data is separated by tabs instead of commas. And it's highly configurable, allowing you to, read different data types efficiently. This is super helpful when dealing with datasets that aren't in a standard format.
Right, so it's not just about reading the data, it's about understanding how the data is formatted too. What about reading data from, let's say, an Excel spreadsheet?
That's also very straightforward. You use read_Excel. You specify the file path to the Excel file, and Pandas can handle different Excel formats, XLS, XLSX, etc. It automatically infers the sheet you want to import, or you can explicitly specify the sheet name.
That sounds really powerful. So by understanding these features, traders can effectively gather the necessary data for their strategies from a variety of sources and use it for analysis?
Precisely, Monsieur. This capability allows traders to create, robust, adaptable trading systems that can be flexible based on the availability of different data sources. And like we discussed earlier, the analysis part is just as crucial as the data gathering part. Pandas is great for data handling and manipulation in this stage of the process too.
Welcome back to the show, Yves. We're diving deeper into this Python for Algorithmic Trading book now. We're looking at a CSV file of Apple stock prices from April 2020. So, this data set, can you explain how this initial section is setting the stage for what's to come?
Sure, Matthew. This part, it's laying the groundwork for actually working with the data. We're not just talking about abstract concepts. We're seeing how Python interacts with real-world financial data. We're looking at a CSV file, that's a comma-separated values file, a common format for storing tabular data like this.
Right, so it's not raw data floating around in the air. It's something tangible. So, this snippet shows us, the beginning of working with this file. What's the Python code doing? Can you break down the crucial steps?
Absolutely. The code snippet starts by defining a file path to the CSV file using fn equals /data/aapl.csv. This line of code assigns the string /data/aapl.csv to the variable fn. This path assumes that the file aapl.csv is located in a folder called data, which is one level above the current working directory. You'd adjust this path if your file isn't in that location. It's critically important to get the file path right.
Got it. So we're assigning the file path to a variable. What happens next?
Next, it uses a with open statement to read the file. That's crucial because it ensures the file is automatically closed even if errors occur. The R specifies reading mode. Then it uses a for loop to iterate over the file, specifically limiting the loop to the first 5 lines.
So we're reading a specific number of lines, not the whole file. That's important in practical terms, right?
Exactly. This way, we can quickly inspect the data without loading the entire dataset into memory all at once, which can be huge in large datasets. It's efficient and avoids potential memory errors.
And what does the code print?
It prints the first 5 lines of the CSV file, including the header row. The header row, date, high, close, low, open, count, volume, tells us the column names. This example gives us a peek at the structure of the data, like, understanding that the entries under each column are all financial indicators: date, open, high, low, close, count, volume.
So, the crucial point is that we're getting a snapshot of the data and seeing the structure. This is helpful to understand the format before we start working with it. It's very pragmatic and helpful for knowing what columns we have to work with.
Exactly. The code displays that it's a CSV file, and we have the header row and then the data rows with the Apple stock price information for different days in April 2020. This initial step is a critical first look at the data before embarking on more complex analysis. We know we have dates, high, close, low, open prices, and volume.
Welcome back to the podcast, Yves. We're diving deeper into Python for algorithmic trading, and specifically, how to handle CSV data efficiently. We were just discussing using the CSV module in Python. Now, you've introduced CSV.dictReader. Can you elaborate on how it improves upon the CSV.reader approach?
Sure, Matthew. CSV.reader gives you a list of lists, which, while workable, can get messy, especially for calculations. Imagine you want to calculate the average closing price. You'd have to index into the nested lists, making the code less readable and prone to errors, particularly with larger datasets. CSV.reader transforms each row into a dictionary.
So instead of lists, you get dictionaries? That's a huge improvement for readability and structure. Can you give us a simple example to show the difference? Maybe with a sample CSV?
Absolutely. Let's say you have a CSV file with stock data, including columns like date, high, low, open, close, count, and volume. CSV Reader would give you a list like this: date, high, October 26, 2023, 120. With CSV.reader, each row, apart from the header, is converted to a dictionary. For example, the second row might look like date, October 26, 2023, high 120.
So, the key is you can access the close value directly via the close key. How does this directly aid in calculations?
Precisely. To calculate the average closing price, you now access the close column using the key, which is much clearer. You don't have to worry about list indexing. For example, the code from the previous chunk that calculated the mean sum, float, one close for one in data, /len data, directly uses the close key within the dictionaries. The code becomes cleaner, easier to understand, and less prone to errors.
That's a significant improvement, especially for financial data analysis. You mentioned pandas. Why is pandas preferred over even the CSV.reader approach, given how much cleaner reader already makes things?
CSV.reader is certainly a step up from CSV Reader, but pandas goes even further. Pandas builds on this by creating data frames, which are tabular data structures. These data frames are incredibly powerful for data manipulation. They provide vectorized operations, meaning you can perform calculations on entire columns at once, drastically speeding up complex operations. And they offer advanced functionalities for handling missing values, data cleaning, and data visualization, making working with large datasets and time series data, like stock prices, significantly more efficient and intuitive.
So, pandas leverages the efficiency of vectorized calculations?
Exactly. You can calculate the average closing price, for example, with a single line of code using pandas, making your Python code even more concise. That really speeds things up, especially when you're dealing with large datasets and complex calculations, like many trading strategies involve. The code is easier to maintain and understand, and you get better performance too.
This is incredibly helpful. Thanks, Yves. For our listeners tuning in, this underscores the importance of choosing the right tool for the job, especially in finance where efficiency is paramount. So, CSV.reader is a great step forward from CSV.reader, but pandas takes things even further by providing higher-level tools. Great insight, Yves.
Thanks, Matthew. It's all about leveraging the right tools and techniques for optimized and efficient Python for algorithmic trading.
Welcome back to the show, Yves. We're diving deeper into Python for algorithmic trading, and today we're looking at using pandas to handle financial data. So, we're talking about reading in CSV files, right? Specifically, Apple stock price data.
Yeah, absolutely. We're using pandas read_CSV function. It's a powerful tool for importing data from CSV files, and it's a key part of any algorithmic trading strategy. Crucially, you can customize it quite a bit, which is important for getting your data exactly as you need it.
Okay, so read_CSV. It's returning a data frame. Can you explain what a data frame is in this context?
Sure. A data frame is essentially a table, a structured way to represent your data. In pandas, it's the central way we work with tabular data. Think of it as a spreadsheet within Python. It's got rows and columns. You can access data in rows and columns using various methods, and pandas provides a lot of ways to analyze and manipulate this data.
So, you're saying it's like a structured spreadsheet, and it's very useful, especially for financial data?
Exactly. You've got your different columns for things like high, close, low, open, volume, and the dates, all neatly organized and ready for analysis.
Right.
That line reads in the CSV file named in the variable fn. The index underscore call equals 0 is telling pandas to use the first column as the row index, which in this case is the date. Crucially, parse underscore dates equals true tells pandas to automatically convert the date strings in that first column into proper datetime objects. This is really important, because you can't perform date-based calculations on strings. You need the actual date objects.
So, this is a very useful conversion step. And then what's the next line? Data.info.
That line, data.info, is really useful for getting a quick overview of your data frame. It shows you things like the data types of each column, how many non-missing values are in each column, and how many rows are in the data frame. So it's giving you a summary of your data. It's really important to check this, to make sure the data has been imported correctly and that you have no missing values.
Got it. And then data.tail. What does that show us?
Data.tail shows you the last few rows of your data frame. In this case, it's the last 5. It's handy for a quick check to see if the data looks as expected and to visually inspect the last few data points.
Okay, and then finally, data close.mean. What does that do, and why is that useful in this context?
That calculates the average of the close column, giving you the mean closing price for Apple stock over the period covered by the data. It's a simple but powerful descriptive statistic, and it's very useful for getting an overall sense of the price trend. You could use this to compare to other companies or periods.
Great. So we're importing data, understanding the structure, checking the data, and then getting some basic statistics. This is a fundamental workflow for data analysis within algorithmic trading. It's crucial to make sure the data is clean and well-structured before you perform more advanced analysis and model building, right?
Exactly. And importantly, Pandas significantly speeds up and simplifies these tasks compared to using the Python standard library, making this a more efficient and reliable way to work with financial data.
All right, Yves, so we're diving deeper into how Pandas handles exporting data. We just saw Pandas can export data to Excel and JSON, right? Can you walk us through the practical implications of this?
Yeah, absolutely. This is really handy when you want to share your data with people who aren't necessarily Python programmers. CSV is great, but Excel and JSON are even more common formats, especially in finance. So, Pandas gives us the tools to do that seamlessly.
Okay, so you're saying instead of just CSV, we can now directly create Excel spreadsheets and JSON files directly from our Pandas data frames?
Exactly. It's a single method call. Instead of writing out every row and column manually, _Excel handles the whole export. For example, to save the data frame data into an Excel file named AAPL_XLS in the data folder, and name the worksheet as Apple, we use data_Excel, data/AAPL_XLS, Apple. It's really straightforward.
And for JSON, it's just as easy.
Absolutely. Data._JSON, data/AAPL.JSON does the trick. It creates a JSON file from the data frame. That's a huge time saver for data sharing. What's really cool is that Pandas is handling the underlying serialization into the right format.
That's clear. But, what are the advantages of using a file format like JSON over others like CSV, for example, in financial data?
Well, JSON has a structured format, so you can easily parse and process the data from the file using various programming languages. CSV is simple, but it doesn't offer the structured details of JSON. For large datasets, the hierarchical structure of JSON can improve the speed of data processing. And in finance, often you're dealing with nested data, and JSON is ideal for that.
Interesting. And what about the Excel export? You mentioned Zwings. Why would we use that instead of just the basic Pandas export?
Right, Zwings lets you interact with Excel directly from your Python code. It's not just about dumping the data. With Zwings, you can automate tasks within Excel, like modifying existing spreadsheets, creating charts, or even running Excel macros from your Python code. That gives you way more control and flexibility. It opens a whole new dimension to automating financial analysis and reporting.
So it's not just saving to a file. It's opening the file?
You can do that too. You can connect to an open Excel workbook, write data to a specific sheet or cell, or add formatting. It's like having a Python interface to an Excel spreadsheet, and that's huge in financial contexts.
That's super useful. Thanks, Yves, for these insights. Hey Yves, welcome back to the show. We're diving deeper into Python for algorithmic trading, And in this segment, we're looking at reading data from different formats beyond just CSV files. So, we're now looking at Excel and JSON. Can you walk us through how Pandas handles these?
Sure, Matthew. As we discussed previously, Pandas is incredibly versatile for data manipulation, and that extends to reading various data formats. Now, for Excel and JSON files, the approach is really similar to what we saw with CSV. You use the pdRead_Excel function for Excel files and pdRead_JSON for JSON.
Okay, so it's just a different function call. Let's break down the example for Excel. You have data_copy_1 equals pdRead_Excel, data/aapl.xls, Apple, index_call equals 0. What's the significance of the AAPL argument there?
That's crucial, Matthew. AAPL specifies the sheet name within the Excel file. You see, Excel files can have multiple sheets, so you need to tell Pandas which sheet you want to read. In this particular case, the Apple sheet from the AAPL.xls file will be loaded, and the index_call equals 0 part sets the first column as the data frame's index, making the date column the index, which is often desirable in time series data.
Got it. So, the file path is specified as an argument, along with the sheet name, and you even specify the index column. That makes a lot of sense. What about the JSON file?
The JSON approach is very similar. You use pdRead_JSON, data/aapl.json to read the data. It directly interprets the JSON structure into a data frame.
Interesting. And then, we see the .head function used in both cases. What does that do?
That displays the first few rows of the data frame, in this case, the first 5 rows, giving you a quick snapshot of the data. It's really useful for checking if the data was read correctly and what the structure looks like.
Excellent. So, you're essentially telling Pandas where your data is located, which part of the Excel sheet or the JSON file you want to read, and then making sure the data is loaded in the desired format.
Exactly. And you know, Pandas is pretty robust. If the file format is unusual, like using a different delimiter than a comma, or having specific data types that require special handling, Pandas will usually have an argument or method to handle those situations in the function parameters.
That's great to know. The examples show reading the data into new variables data_copy_1 and data_copy_2. What do you think is the reason for that?
Well, that's a common practice to keep copies of the data. Imagine if you make changes to data_copy_1, you don't want to accidentally affect the original data source. Separating it into copies allows safe experimentation and avoids unintended consequences. Also, you might have different analyses requiring different copies of the data, so this is a fundamental principle in data handling.
Okay, that makes perfect sense. So, the takeaway here is that Pandas really streamlines reading data from Excel and JSON, providing a flexible and robust way to work with financial data from various sources. Thanks, Yves.
You're welcome, Matthew. It's been a pleasure.
Welcome back to the show, Yves. We were just discussing the importance of data in algorithmic trading, and now we're diving into open data sources. This Quandl platform seems pretty crucial, right?
Absolutely, Matthew. It's a game changer for anyone starting out in algorithmic trading. As we mentioned before, access to quality data is often a barrier, but Quandl provides a central hub for a lot of free and some paid data. It's significantly more accessible than trying to cobble together data from multiple disparate sources.
So, the Python wrapper package makes it really easy to interact with this data, right? Can you explain how that works?
Precisely. The Quandl package acts like a translator, allowing Python to understand and request data from Quandl's API. It's a beautifully designed wrapper. You're not dealing with raw API calls. Instead, you use Python commands to fetch data. For example, to get historical Bitcoin data, you import the Quandl package and use a function like queued_get bchan/mkpru, API_key equals. That's a key component. You specify the data source, bchan/mkpru in this case, and provide an API key.
Okay, and the API key, is that something you create yourself?
You need a Quandl account. They offer a free tier that allows you a certain number of free API calls and gives you a unique API key. It's quite easy to set up, and you can access that key in your account settings. Crucially, The code snippet also shows how to read the API key from a configuration file, like pyalgo.cfg, using the config parser module. That's a best practice to keep your API key secure, right out of the codebase.
So, you store the key securely and use config parser to retrieve it, which is excellent for production environments. Now, the code snippet retrieves historical average Bitcoin prices. How does that part work? In terms of extracting and formatting the data.
Right. The q.get function, returns a pandas data frame. This is fantastic because pandas makes manipulating and analyzing the data incredibly easy. The data.info part gives a summary of the data, the dates it covers, the column structure, and the data types. Then, using .resample at last, you transform the daily data into yearly data by taking the final value in the dataset for each year. This gives a yearly end-of-year perspective, though it's important to be aware that, the 2020 value might not be precisely the year-end value, just the last recorded data point.
You pointed out that some free datasets require an API key, after hitting some API call threshold. That makes sense. And are there any examples of retrieving data for other types of financial data, like individual stocks?
Absolutely. The code demonstrates getting SAP stock prices using similar syntax but specifying the dataset, FSE/SAP_X. You can also specify a start_date and end_date to narrow down your data. The example then reveals the structure of the retrieved data. It provides, for example, open, high, low, and closing prices, volume, and other indicators. In certain cases, some data might not be present due to missing records, so the program provides a robust analysis structure to accommodate such cases.
So, it's not just Bitcoin data. You can get stock data, options data?
Absolutely. The example shows how to pull option implied volatilities for Microsoft, demonstrating the breadth of the data available. And this whole example shows that you can adjust the code to get almost any financial data you need. This is precisely what makes Quandl such a useful tool for algorithmic trading, providing readily available, diverse data.
Excellent. Yves, this has been fantastic. Thanks for clarifying the use of Quandl and its Python wrapper, Quandl. We'll be back after the break with more on this fascinating subject. Hey Yves, welcome back to the show. We were just talking about how open data sources, while great for beginners, eventually become insufficient for serious algorithmic traders. Now, you're highlighting Refinitive's Icon Data API, right? Can you tell us more about how this API works for more advanced traders?
Absolutely, Matthew. Icon, as you know, is one of the major players in financial data provision, offering petabytes of data through a unified platform. The desktop version is powerful, but the real advantage for algorithmic traders is the API. It allows for programmatic access to that vast dataset, which is crucial for automated strategies.
So, you're saying it lets us pull data directly into our Python code without manually downloading and cleaning it ourselves?
Precisely. The crucial piece is the Python wrapper package called Icon. It's installed via pip install icon. This makes interacting with the Icon API significantly easier than with raw API calls.
Okay, so we've got the package. What's the next step? How does the Python code connect to the Icon data?
You need a subscription to Refinitiv Icon Data Services. Then, you'll need an app_key.
So, the app_key is a vital component of the API access?
Absolutely. You have to set that key within your Python code. You'll see something like ect_set_app_key, config icon, app_key. This line sets the key retrieved from your configuration file to enable the API connection. The config object holds various settings, such as the app key, for security and easier management.
This ect.set_app_key line is critical for security, preventing unauthorized access to the data.
Right, it's a crucial security measure. Then once you've connected, you can use the icon packages functions to retrieve historical data, stream structured data, like price quotes, and potentially even unstructured data, like news feeds.
So, with the API connection secured, we can then start building our trading strategies by requesting the needed data.
Well, you can get historical stock prices, fundamental financial data, like earnings reports and balance sheets, news headlines relevant to your target stocks, and more. The possibilities are vast, allowing you to build sophisticated trading algorithms based on your strategies.
That's a lot to unpack. You are suggesting that this Python wrapper essentially acts as an interface, making complex data retrieval more straightforward?
Exactly. It handles the intricacies of the API interaction, allowing you to focus on the logic of your trading strategies, rather than the low-level API details.
Great, Yves, this is immensely helpful. So, we now have a clearer picture of the Icon API's integration with Python. We'll dive further into specific use cases next time. Thanks for this in-depth look. Welcome back to the podcast, Yves. We're diving deeper into Python for algorithmic trading, specifically looking at retrieving historical financial data. We were last discussing how easy it is to get time series data from Icon. Can you elaborate on the flexibility this offers, particularly when you need different granularities?
Absolutely, Matthew. The key here is that the get_time series function isn't just limited to daily data. You can grab data at the minute, hourly, or even tick level, which is crucial for highly dynamic markets. For example, if you're looking at extremely short-term trading strategies or trying to analyze order book activity, tick data is essential.
Right, that makes sense. So, you're saying we can get down to the individual trade level? How is this handled in the Python code?
Exactly. Let's look at the example. When you set interval equals minute, you're asking for data recorded every minute. This is what the code does in line 45. It's efficient for getting a large amount of data, though it will obviously be far larger than daily data.
Interesting. And what's the impact of retrieving data at a higher frequency, like in the minute interval or tick data, compared to daily data?
Well, you're dramatically increasing the volume of data. Remember, daily data summarizes all trades in a day. In minute or tick level data, you get the price and volume every minute or each trade. This provides a much more granular view of market movements. However, dealing with huge datasets is critical. You need to consider the computational costs and the storage requirements, as well as potential latency issues during data acquisition.
So, you mentioned latency. What else do you need to be aware of?
Handling the potential for irregular time intervals is crucial. Let's look at the tick example, 48. With tick data, you get trades at different times, not at perfectly regular intervals. So the times between trades might vary significantly, leading to non-uniform sampling.
That makes sense. This is why you then resample, right? Like in line 51, data.resample 30s.
Precisely. Resampling, using resample 30s, label equals right, allows you to group data into 30-second intervals. For example, it might take the last value and aggregate the volume within each interval. You could also use other aggregations, like calculating the average or maximum price within each interval. Crucially, the label equals right tells the function to label the interval based on the rightmost timestamp within the interval, not the leftmost. This is important for getting the correct data labeling.
That's great. So, using resampling lets you create intervals of time for easier analysis, and you can also use various aggregations for your needs. This is really helpful in data analysis, right?
Exactly. Understanding the time resolution, the data volume, and the handling of irregular intervals are critical for effective algorithmic trading strategies built on historical data. You need to think through these details carefully before diving into complex computations or models.
Welcome back to the podcast, Yves. We're diving deeper into leveraging the Icon API with Python for pulling unstructured data. Specifically, we're looking at news headlines. You mentioned this is pretty straightforward, right?
Absolutely, Matthew. It's actually remarkably similar to how you'd get financial time series data. The key is the API structure and the Python wrapper you're using. You're essentially issuing a query, defining what you're looking for, like news about Apple and MacBooks within a specific date range, and then the API delivers the results.
So, the code example shows us using ec.get_news_headlines. Can you walk us through the essential components of that function call?
Sure. ect_get_news_headlines is the function, and within the parentheses, we're providing several crucial parameters.
First, query gleich er, APL, o MacBook. This is a search criteria.
The R prefix tells Icon that we want to search for news related to the ticker symbol AAPLO, which is Apple, and the keyword MacBook. This kind of focused query is really powerful.
And what about count equals 5?
count equals 5 specifies that we want a maximum of 5 headlines returned. It's crucial for controlling the amount of data, especially when dealing with potentially large result sets.
Excellent. What's the role of date_from and date_to?
Those parameters, date_from equals 2020-4-1 and date_to equals 2020-5-1, define the date range for the search. So in this example, it's looking for news between April 1, 2020 and May 1, 2020. A critical component for analysis focused on a time interval.
Interesting.
Exactly. You're not just getting everything, you're filtering it down to the relevant information, news from that time frame about that specific topic.
And the output, headlines, appears to be a structured data object?
Yes, it contains the headlines found and, importantly, associated metadata, the date and time the headlines were created, their unique identifiers, and the source code, which often indicates the publication where the news came from. This structured data makes it possible to then further analyze, process, and extract deeper insights from the news.
So after we have the headlines, you illustrate how to extract the details of a particular headline, like the content.
Exactly. We pick a specific headline using headlines to iloc 0. Iloc is a pandas function to get a specific row based on its numerical index. Then you can extract fields like the headline text, story, the story identifier, story ID, and potentially source details, source code, giving you a very granular view of each news item.
That's insightful. And then, finally, ec.get_news_story fetches the full news article, which you demonstrate with HTML rendering.
Correct. ect_get_news_story takes the story ID as input and returns the full news article. That's useful for in-depth analysis.
So, the key takeaway is that, using Python and the Icon API, we can access a wealth of news data. We can set up precise searches, control the amount of data retrieved, and analyze specific news stories. This is invaluable for stock market analysis and algorithmic trading strategies.
Precisely. And it's all very straightforward to implement.
Welcome back to the show, Yves. We're diving deeper into efficient financial data storage, specifically in the context of algorithmic trading. So, we were talking about this retrieve once, use multiple times principle. Can you elaborate on the practical significance of that in the trading world?
Absolutely, Matthew. It's a crucial concept. Imagine you have a massive dataset from a web service, like historical stock prices. You might need to use that data to backtest various trading strategies.
Right. So, in effect, you're minimizing the redundant downloads or repeated data pulls. Makes sense. Now, you mentioned write once, read multiple times as well. Can you elaborate on that?
Sure. You often get continuous data streams, like real-time stock tick data. Instead of keeping it all in memory, which can be extremely demanding, you write it to disk, to a file or a database. Later, when you want to analyze this data, you can read it many times for various calculations like aggregations or correlations. The critical part is that this data is written once, and then used many times. This is far more efficient than retrieving the live data each time. This is especially vital during high-frequency trading situations.
Okay, that's clear. You also mentioned pandas data frames for these data structures. Why is this choice preferred in this context?
Pandas is a fantastic library in Python for data manipulation and analysis. It's specifically designed for tabular data, like the financial data we're discussing. It provides optimized data structures that allow for fast access and manipulation of rows and columns, which is essential for our scenario. Also, Pandas handles missing values, data cleaning, and transforming data effectively, very useful in the financial world.
Excellent. And then you showed us a sample financial data set generated with generate_sample_data. Could you explain how this function works and why it's relevant to the conversation?
The generate_sample_data function, from the provided Python script, creates a representative sample of financial data. It's useful for demonstrating concepts and testing code without needing to download or access real data sources. It generates synthetic data quickly and efficiently, allowing us to experiment with different data structures and calculations without relying on external or possibly expensive data feeds. It has arbitrary rows and columns to demonstrate scalability. You can set the size, rows and columns, to make your data manageable depending on the scenario and the computing resources.
So, it's essentially a mock data set. I see. The output shows a data frame. So, what are the rows and columns representing?
The rows are time series data, representing the price of the asset at different points in time, while the columns presumably represent different characteristics, like price, volume, or other relevant factors. In this case, the columns are labeled No1, No2, No3, and No4, each with their values.
Got it. So, having this synthetic data allows us to practice and develop our strategies without using live, potentially expensive, real-time financial data. This really helps with development and testing, especially for optimization scenarios, right?
Precisely, Matthew. Testing different strategies on simulated data is crucial for performance and validation. By using synthetic data, we avoid potential risks and costs associated with real-world data.
Welcome back to the show, Yves. We're diving deeper into Python for algorithmic trading, and today's topic is storing data frame objects. You mentioned using HDF5 for this, right? Can you elaborate on the process?
Absolutely, Matthew. Storing large data frames in memory can be a bottleneck. So using HDF5, a binary format, is a great way to get around that. The PDHDF store is a convenient wrapper provided by pandas.
So, we're talking about a file-based database. Can you explain the example? The chunk details a 420 megabytes data frame.
Yes, the example shows generating a sizable data frame, a sample financial dataset with 5 million rows and 10 columns. The code, while not shown here in full, would generate this data. We then store the entire data frame into an HDF5 file on disk. This process is pretty crucial for performance, especially for huge datasets.
You mentioned the data frame is about 420 megabytes, but the HDF5 file is a bit bigger.
Yeah, usually the on-disk representation of a data frame in HDF5 will be slightly larger than the in-memory version because of how data is structured and stored, but you do gain much faster writing speed, often 5 times faster than creating the data frame directly in memory. And the speed of writing to disk approaches the maximum speed of your hardware.
That's interesting. So, the writing process isn't bottlenecked by memory.
Exactly. It's a key takeaway, Matthew. You're writing directly to a binary file, which is a much faster operation. The example demonstrates this clearly.
How does reading from the file work? Is it just as fast?
Yes, reading is also very fast, almost as fast as the writing speed. The example code for reading shows this performance too. You open the HDF store in read mode, extract the data frame, and get the data you need quickly.
That's great. You mentioned 2 approaches for saving data to HDF5. Can you contrast them?
Sure. The first approach uses PDHDF store to write the whole data frame at once. It's faster for complete data sets that fit in memory. The second approach, using data frame _HDF, allows for appending data and other more advanced functionality. You can, for example, search data on disk, which is handy for data that's constantly being updated or for much larger sets that aren't all in memory at once.
But it's slower for a single write, right?
Yes, using to_HDF, with format equals table, is slower compared to the HDF store method for a single write. It adds overhead because it has to handle writing to a table format. And the file size is slightly larger too. But this format is essential when you're working with tables that need to be updated and appended, making it great for continually growing datasets.
So, in the example, there's a bit more flexibility with dataframe._HDF. It's good for dynamic datasets.
Exactly. It integrates with the Pytables library, giving you access to more advanced table manipulation functionalities. You can append rows to the HDF5 table using Pytables capabilities.
And the example in the chunk shows accessing the data within the HDF5 table structure using Pytables?
Precisely. The example code shows how to import Pytables, open the file in read mode, display file metadata, and get the first few rows of the data frames table. It gives you a clear view of the data structure and contents of the HDF5 table, a critical aspect of using Pytables.
You've really highlighted the advantages and disadvantages of each method. So, for a massive dataset that's constantly being updated, the to_HDF method with format equals table is the way to go, but the other one is faster and simpler for static data.
Precisely. And exports to CSV files, as you noted in the chunk, are generally a much slower alternative to HDF5 for large datasets.
Welcome back to the podcast, Yves. We're diving deeper into this Python for Algorithmic Trading book, specifically the TS tables package for handling large financial time series. So, we were talking about how it builds on pytables, right? Can you give us a little more detail on how TS tables enhances the capabilities?
Absolutely, Matthew. TS tables is a really useful extension of pytables. Pytables itself is a wrapper around HDF5, which is a powerful binary storage library. Pandas uses HDF_, which is essentially an interface on top of this HDF5 library for storage. TS tables takes that further, specifically focusing on massive time series data, especially financial data. It's optimized for efficiently handling that kind of data. A key advantage is its hierarchical storage structure. This allows for super-fast retrieval of specific subsets of the data, based on dates and times. Think of it as a sophisticated filing system for financial time series.
That's helpful. So, you mentioned faster retrieval. Can you elaborate on the write once, retrieve multiple times strategy?
Right. Imagine you're constantly pulling financial data from a source like a web API or a professional data provider. You collect this data, often storing it in a pandas data frame in memory. Now, before that data frame gets too big, and you risk losing performance or having memory issues, you write that data into the TS tables table in the HDF5 database. The core idea is to efficiently store this data for later use. Subsequently, you can retrieve exactly the data you need, potentially pulling out a smaller subset of the entire dataset when needed for your analysis. This greatly increases the processing speed and reduces memory usage.
Okay, great. You described generating a sample dataset of 2.5 million rows. Can you explain the code snippet that creates this data?
Sure. The code you mentioned there is creating a large pandas data frame. It uses the generate_sample_data function. It's important to understand that rows equals 2.5 E6 means it's creating 2.5 million rows. The function will generate that data with 5 columns, and specified frequencies, and I believe, rounded to 4 decimal places here. The time efficiency is important, as shown by the %time magic command in IPython.
So, it's not just about efficiently storing the data, but also efficiently creating it in the first place.
Exactly. It shows that the code for generating the data takes a noticeable amount of time. This is a critical aspect of understanding data handling with large datasets. How long does it take to generate the data? How long does it take to load it? How long does it take to query it? These are all questions you need to consider when dealing with large datasets.
Excellent point. Moving on, you mentioned a desc class. What does this do?
The desc class defines the structure of the TS tables table, essentially acting as a schema. It specifies the different columns in the table and their data types. For example, it says the first column is a timestamp, represented as an integer. All other columns are floats. This information is critical for TS tables to properly interpret and write data into the table. This method of using a class is cleaner and better structured.
Makes sense. Then, the code creates the table in an HDF5 database. What's the key takeaway about this process and its efficiency?
The process is fairly straightforward. It creates the database, then defines the table structure and creates the TS table object itself. The fact that TS tables chunks the data into daily subsets is quite efficient. By storing a day's worth of data at a time, it ensures that you can easily retrieve the data associated with a particular day when conducting analysis.
Right, and the append operation seems remarkably quick too.
Absolutely. The TS append data line is the core of the append operation, using a simple method call to append the data frame's data to the HDF5 table. It's not just convenient, it's optimized for speed. This is a significant advantage of TS tables, especially in high-volume financial data situations.
Finally, retrieving data subsets with the read_range method is also very efficient, isn't it?
Yes, querying the specific ranges of time is done through the read_range method. It's extremely fast, taking only milliseconds to retrieve the data for specified start and end times. This really emphasizes how TS tables is optimized for these kinds of queries. The function even returns a pandas data frame, making further data manipulation a breeze. It's designed for typical backtesting applications in algorithmic trading, where you need to rapidly access specific historical periods of data.
Welcome back to the show, Yves. We're diving deeper into Python for algorithmic trading, and specifically storing data. So, we've established that using SQLite 3 for financial time series data isn't as speedy as binary formats like HDF5. Can you elaborate on why this is and the trade-offs involved?
Absolutely, Matthew. You're right, relational databases like SQLite 3, while excellent for querying, introduce overhead in terms of writing data compared to binary formats. That overhead comes from the fact that SQLite 3 needs to convert the data frame's data into a structured table format, which involves some extra processing. Think of it like translating a document from one language to another. It takes time. The binary formats, on the other hand, just store the data in its native form.
So, the example shows a significant time difference when writing to the database, 4 seconds as opposed to milliseconds or less for binary storage. A big difference. Why does this happen? What's the key factor at play?
It's the conversion process, Matthew. The to_SQL method, used to write to SQLite 3, has to translate the pandas data frame structure, with its indexes, data types, and other metadata, into the database's format. This translation takes time, especially with large datasets. Also, SQLite 3 itself has internal operations to manage the database file, which also contribute to the overall time taken.
Okay, so the time cost is primarily from the translation process and SQLite's internal mechanisms. But the example then showcases how to use SQL queries with this data. Isn't that a significant benefit? How does that work out in terms of speed?
Absolutely. The real strength of relational databases like SQLite 3 comes when you need to perform complex analytical tasks. SQL is incredibly well suited for filtering and aggregations, which you might not want to do directly in your pandas data frame, especially if your data is massive. This is why our example shows that executing SQL queries to fetch data can be very fast, especially compared to doing the same thing within pandas if it's loaded into memory.
So, the SQL query to select rows where the no1 column is between 105 and 108 takes a relatively short time. Does that mean SQLite 3 is the way to go for any query of this type?
Well, it depends on the data size and the complexity of your queries, but it's often a good choice, especially when working with large datasets that don't fit in memory. You're right, the example shows that simple queries, like the one selecting based on ranges, are very fast. However, complex queries with aggregations and joins could still potentially take longer.
Great insights, Yves. So if the speed is better for complex queries with SQL, what are the trade-offs, especially when dealing with enormous datasets that won't fit in memory?
You're touching on a critical point, Monsieur.
While SQLite 3 shines in these cases, the disk space required is considerably larger for a relational database compared to a binary format. In the example, we see a 100+ MB database size. The efficiency of queries is often balanced with the storage and access time cost.
So, the key takeaway is that SQLite 3 excels when speed of retrieval is critical in complex analyses on large datasets you cannot fit into memory, but binary formats like HDF5 are more efficient if speed of writing data is paramount and storage space is not a major concern, right?
Exactly. It all boils down to trade-offs, understanding what you're trying to achieve, and considering the specifics of the situation.
So, Yves, we're diving deep into handling financial time series data, right? This chapter sounds crucial for building trading strategies. Can you give us a quick overview of why reading data from different sources is so important?
Absolutely, Matthew.
It's fundamental.
You need to be able to grab your data from various places. CSV files are common, obviously, but you also need to get data from APIs like Quandl. This gives you access to real-world market information, including end-of-day prices and option data, which is critical for a lot of trading strategies. And it's not just about the data itself, it's about having the flexibility to choose the source that best fits your needs. For instance, you might need historical data for backtesting from a CSV, but current data from a live API for real-time strategies.
Right, that flexibility is key. And Quandl, you mentioned it. It's a really popular choice, isn't it? Why is it a good source, and what makes its API stand out?
Yeah, Quandl's great. It's got a huge library of publicly available financial datasets. You've got everything from stocks and bonds to commodity prices and economic indicators, all under one unified API. You just specify what you need, and it pulls it in. That's a huge advantage over trying to piece together data from multiple sources. The API design is pretty straightforward. It makes accessing and processing that vast amount of data really efficient.
Okay, so we've got the data in. Now how about storing it effectively? You mentioned storing complete data frame objects. Why is that important? And what are these HDF5 and SQLite 3 databases?
Storing data frames directly is often much faster than loading and processing data repeatedly. Imagine having massive datasets. If you load them every time you need them, that slows things down. Storing them in an HDF5 file or SQLite database is akin to having a persistent copy of your data frame, so you don't waste time reloading. Both HDF5, a file-based storage format, and SQLite 3, a lightweight relational database, are great for this because they both offer efficient storage and retrieval, especially when you've got large data volumes. HDF5 is particularly good for numerical data, and SQLite is a more versatile option for structured data, which can be a better fit in certain circumstances.
So, HDF5 for numerical data and SQLite for structured data. That makes sense. Is there a particular circumstance where one might be preferred over the other?
Well, if you have a really massive dataset or if speed is your primary concern, HDF5 often shines. But if you have a lot of different data types or need more robust data management tools, like joins and queries, SQLite might be a better choice. It depends a lot on the specific nature of your project and the volume of your data.
Excellent. You've highlighted the importance of getting and storing data efficiently. It's crucial for the chapters following, right? Like backtesting and machine learning?
Absolutely. These techniques rely heavily on having ready access to clean, well-structured data. By focusing on data handling now, we set the stage for robust and efficient algorithms and models in the subsequent chapters. The data preparation and access discussed here are foundational to the practical application of what we'll explore in the next 3 chapters.
Perfect. Thanks, Yves. That really clarifies the importance of proper data handling for algorithmic trading.